Hello, F Sharp. Welcome back. We are continuing our journey of improving a topological sort algorithm, specifically the cons algorithm. And like I've mentioned in previous videos, this is the hottest piece of code in a simulation engine I am working on for my company. And so it's very important that it is as fast as possible, because the faster it is, the more simulations we can do, the more things that we can analyze, the better understanding we're going to have. So where did we leave off last time? So what I have up on the screen right now is the progress that we've made. We had the naive version, which for 1,000 graphs of the size that we're interested in, it took 59 milliseconds. We then went through and made some improvements to it and got it down. Well, what we did is we changed the way we modeled the domain so that we moved some of the computation into how the domain itself was represented. And that gave us a significant performance improvement, and that got us to 37 milliseconds. Now remember, ideally, we want to be able to solve 1,000 graphs in 500 microseconds. But that's kind of the general idea of what our ultimate target is. That number is a little fuzzy because it'll depend on what CPU you're running on, but that's the general idea of what we're targeting. That's our ideal scenario. We then made an improvement from version 2 to version 3 by swapping out the F-sharp map collection for a read-only dictionary. And instead of using the F-sharp set, we are using a hash set for our algorithm. And one of the things that was important is that, yeah, we started using a mutable collection, but that collection never leaks outside of the bounds in which it is used. And so that's one of those design principles of F-sharp, that F-sharp is absolutely fine with mutation. The idea is that mutation is isolated and it's contained and it doesn't leak outside of boundaries, because there are scenarios where mutation is simply the fastest way to do something. And that's what we saw. And that took us from the 37 milliseconds of version 2 to now 9 milliseconds for version 3. So we've made a lot of progress, but we're still pretty far from where we would like to get. So today what we're going to do is we're going to profile version 3, make some observations, change the algorithm, and see where we get. So for me to profile this, I'm going to use .trace. And the way the program is set up, and I'm going to show this here really quick. Oh, let me zoom out because I'm a little zoomed in. So the way this works is when I want to, again, let me zoom out a little bit more to make it easier to read. When I want to profile something, what I do is I'm using the library called argu, A-R-G-U, for F-sharp. And it makes it really easy to provide command line arguments and parsing. And so what I do is I say hey, I want to profile, and I tell it what method I want to profile. In this case, I want to profile method number version 3, and how many iterations I want it to just repeat that code. And this profiling is running the exact same code as the benchmarks. And you can see that here. What it does is the profile function, it takes the method and the loop count, so how many iterations you want to run. It creates an instance of the benchmark class, and then based on which version, it's just going to run that method over and over and over and over again. Now, the reason we want to do that is so that the CLR optimizes that code as much as possible so that we are able to get an idea of what the performance of a real world use case looks like. So I'm using .trace. See if it comes up. And the setting I'm using is I've provided the path to where the executable is, and I'm providing the arguments where I want the task is to profile. The method is version 3, and I want it to perform 1,000 iterations. So it's going to call that method 1,000 times. And then I'm going to say, go ahead and start. And again, if you want to know more about how to use this tool, JetBrains has some excellent videos and excellent documentation. That's not really the point of these videos. So If you want to know more about that, feel free to go ahead and check out their resources. So we've completed, the program ran, performed 1,000 iterations of that benchmark. And so now we're going to be able to look at what some of those performance numbers are. And so what I like to do is I like to expand this out, and I'm looking at all the calls, and I'm saying, hey, down at domain, I'm going to look at profile and version 3. And so this is the method it's calling over and over and over again. And you see that, hey, this is taking 89% of the runtime. Well, the reason this isn't all of it is because there's some startup code and that is occurring. So that it's not actually 100% of the runtime. Some other things had to run also in order to get to this point to get started. So that's why I like to click down and say like, hey, I'm clicking on the method I'm interested in. And we see on the right, the code that lines up with that method. So we can see like, oh, this is what that corresponds to, which is really nice as a way to verify like, hey, I'm looking at the right thing. Now, one of the things I do in profiling is I like to expand this out. And this view here is really useful for finding if you have a particular function or method that is super hot or dominating the runtime. And what I like to see is it's saying like, hey, this is taking up 89% of the time. 30% of the time is taking on creating that initial edge set. So this is the set of edges that the cons algorithm needs to keep track of. And as it proceeds, it's removing elements from there. And then it's spending 45% of its time in this loop, which is the actual work of the cons algorithm. Is it's going in, checking and say, hey, is there anything I can add to the sorted list of nodes? And when I do that, I remove its edges, and then I say, hey, does anything else need to be processed now? The Wikipedia article is very good in describing the cons algorithm, and I'll have a link in the description. But what I'm seeing here is like, okay, well, there's not a particular function or method that appeared to be, there's nothing that's like a real hot outlier. Sometimes what you will see is like, oh, there's like one function that is absolutely dominating everything else. And I'm not seeing that in particular in this case, but that would be the first thing I looked for. Since I'm not seeing that, what I like to do is just, I'm going to click on this method, and down below there's this really useful information. And what this is doing is it's breaking down how much time that method, the selected method, is spending in the various subsystems. This area up here is a visualization of that. And then down below is more of like this kind of tree view where you can expand things out. So this is nice to kind of have a quick visual check. I really like this tree type of structure where I can go and see like, hey, what is going on in here? And what we're seeing is like, okay, well, it's spending a lot of time in got dictionary quality. So a lot of times spent with dictionary, getting item, try get item, get enumerator. So it's enumerating through it. And there's also a hash set where it's spinning like add if not present, remove, resize. Okay, yep. So it's basically saying, hey, I'm spending a lot of time with dictionaries and hash sets, like looking stuff up, removing things. Like, okay, that makes sense. So anything going on with user code? Also, if you hear noise in the background, my children are out of school. And so there's just going to be a little noise. So I'm going to do the best that I can, which is why I try to acoustically treat some things in order to provide the best experience that I can. But life goes on, and I have children. And yep, sometimes that creates acoustic challenges. So what I'm seeing here is that it's just generally spending a lot of time in these things. And so what I then like to, so here's the other thing I'm noting is that, hey, there's a lot of time here in this compute hash 32. And is this system code? Okay. Computing hashes. Spending a lot of time computing hashes. Interesting. Okay, now let's go look at our domain and see why that might be the case. And again, we are profiling version 3. And let's look at this. right now we're modeling a node as a record, and it has and its name, the name field is a string. And an edge is made up of a source and a target, which are both nodes. And a graph is made up of two read-only dictionaries. The read-only dictionaries in this case have a key of node, and the value is an edge list. And so when I look at this, and then I look at that profiling information, it's like, okay, it's spending a lot of time on hashing. It's spending a lot of time just looking things up and removing things from a hash set and or a dictionary. Well, it's looking up in a dictionary a lot, and it's adding and removing things from a hash set a lot. So the speed of hashing is really critical with the way this is set up. And so the question I then ask myself is, can I model this domain in such a way that is more conducive to fast hashing? Well, the answer is yes. And this is going to come down a little bit to the scenario that I'm working in. So your mileage may vary. You may or may not be able to do these optimizations, but I want to take you through the thought process that I have. So in terms of simulations, a simulation is typically made up of, there's like the modeling phase. So that's the phase where I, as an analyst or a modeler, want to build up a model. I want to build a model, which is a description of the thing that I want to simulate. I then simulate it. I then I take that model and I send it to a simulation engine. It takes that, performs the simulation, and then reports back the result to me. And then the result is typically statistics and information about what transpired. Well, the one of the key things that I've been learning is that I really fell into a rut where I wanted to use the same domain for everything that I did. So the domain I used for modeling, the domain I used for simulation, and the domain I used for analysis, I smushed all of that together into a single thing. And the problem I kept running into is that the needs of those three different workflows are very different. And so when I wrote this initial version, I very much had the analyst point of view in my head, the modeling point of view. And so I wrote a domain that made that as easy as possible. The problem is once you get to the simulation phase, the computation phase, that representation of your problem may not be very conducive to high performance. And that's a little bit of what we dabbled in last week. It's just talking about like, hey, the way you represent data is going to push you in different directions when it comes to composing your solution. So one of the first things I like to do now that I have a little bit more experience and I've done this a little bit more is saying like, hey, would my problem be easier if I changed the representation? Would my problem, I don't know if you care my son, but he's being adorable. Would the computation be easier if I change the representation? And so the answer is absolutely yes. And so I often now create different domains for the different use cases. So I will have a modeling domain, I will have a computation domain, and I will have an analysis domain. And each of those has its own set of types, and there's mappings between them. So the question is, okay, I'm looking at this and say, okay, I need the computation code, the computation domain to be faster than it is right now. And this is still very much a kind of analyst way, a modeling domain way of modeling this domain. These words are very overloaded. My apologies. So hashing, we're doing a lot of that. Are there types that are more conducive to fast hashing, faster lookups, fast in general? And the answer is absolutely yes. The answer I would come away with is, let me bring this up here, and I want to put these side by side. Come Come on. Okay, here we go. I'm going to put version 4 on the left and version 4 on the right, version 3 on the left. So this is what the domain looked like before. And over here on the right, I'm changing things up. I love units of measure in F#. And the reason I love that is because it allows you to add a lot of context to the primitives in F#. Ints, int64, floats, bytes, int16s. Most things are supported. Most numerics are supported right now. So I'm going to change the way I'm representing things because one of the fastest things in the world to hash is an int. Because last time I checked, the hash for an int is just the value itself. So hashing is instantaneous. Inequality of ints is insanely fast. And so comparing that to string is just, it's outrageous, the performance difference. And so I'm going to show you a little bit about how I like to model things now. And I have these side by side so you can kind of compare and contrast what I'm doing. So one of the things I like to do is I like to have a module for the different units that I'm going to use. And units of measure were, I believe, originally envisioned to be used for like algebra. So verifying addition, subtraction, multiplication, and division. But I use them as a way of just annotating primitives to provide them context. I kind of think of it more in a broader sense. So how do I like to use them? Well, that has evolved a lot. And this is kind of showing what my current best practice is. What I like to do is I like to create a private module which contains the units that I'm going to be using. In this case, I'm going to be using a unit of node and a unit of edge. And then outside of that, I like to define an alias, which is saying, hey, what is a node? In this case, I'm going to say a node is an integer that has been annotated with the units of node. And the reason I make units private is because I don't want you to be able to just make this wherever you want. I want you to have to use a function that I'm providing that will perform the necessary validation to ensure that this thing even makes sense. And in my domain, I'm going to have a module, and it's going to have a create function, which takes in an int. And what it does is just the mildest of validation, saying, hey, nodes are only non-negative integers. And so it's checking to say like, hey, is this value, if the value is less than 0, then it's throw an error. Otherwise, like, yes, I'm going to allow this to be a node. Now you might say, hey, Matthew, why aren't you using unsigned int? That comes up later. It's not happening this week. It'll happen later. It has to do with using these things to index into arrays, but don't worry about it for now. So I performed some mild validation. So I am restricting the domain of values that node can take on. And then the same thing for edge. I'm going to do something a little funky here. And this is so before edge, so node, instead of being this name string, node is now just an int with a unit of measure. Edge is going from a record with a source and a target to an int64 with the units of edge. Okay, why that? Well, this is a cheat. No, this is a technique that I learned from Jeremy Chassain. Okay, I can't pronounce that last thing, but he, developer out of France working at D-Wave, and he's just a phenomenal F# developer. I've learned a lot from him. He's very patient with all my questions. And the idea is like, okay, an edge went from being 2 nodes to an int64. How am I doing that? The way I'm doing that is a node is an int. And if I want 2 ints together, well, and an int is 32 bits. If I want to put 2 nodes together, I need 64 bits. Well, what is a natural way of putting 2 32 bits together? 64 bits, int 64. So what I do is I say, hey, an edge is just an N64 units of edge. If I want to create an edge, you need to give me a source and you need to give me a target. And what this is doing is that it's just doing some bit shifting and bit math to create that N64. And the way this works is that the top 32 bits is the source and the bottom 32 bits is the target. And then I have functions for get source and get target. And what it does is that you give me an edge and then I will give you the top 32 bits at the bottom 32 bits as a node. And what this does is it allows for extremely fast hashing. And so these ints and int64s are a faster thing to use with hash sets and with dictionaries, because I'm not aware of something that's faster for hashing inequality checks. And then the rest of the code is essentially the same. If you went and looked at it, the code for the actual loop itself has not changed really at all. We've just changed how we represent edges and nodes. And when we run that benchmark, let me bring the screen right here, we go from 9 milliseconds to solve 1,000 graphs down to 5 milliseconds. So another really significant performance increase. So big deal, huge jump. And this is actually going to enable quite a few more jumps later on, but I needed to add add this new way of representing our domain to enable all those future enhancements. So what's the takeaway for this? I think the key thing, and this is a kind of repeating a little bit from last week, if at all possible, when computation becomes the bottleneck for your work, do everything you can to represent your domain in such a way that is conducive to the computation. This doesn't necessarily apply to like a line of business app that is just like taking in a blob of JSON and then like doing a transform and sending it on. So this is very specific to this kind of work, but this is the kind of work that I do and I love and I get really excited about it and I wanted to share it. So domain representations really matter. And if you can use simpler types, but without losing the domain context around them, that's one of the first things that I do is I say like, hey, do I need to use strings? Can I map it down to ints and 64s? Because I'm now moving closer to the language of the machine itself, and it's going to be able to speak that faster than having to go through these additional levels of abstraction. So I hope that was interesting. I hope that's informative. We got a lot of levels to go from here, but this is a really critical transformation of our code to enable those future optimizations. So if you have any questions, please feel free to comment, hit me up on Twitter or email me. I love this stuff and I want to be making things that are helpful and useful to you. And so until next time, thank you very much for spending some time with me and I look forward to hearing from you. Thank you much. Bye-bye.